Hello, this is Jin Ouyang from the Department of Material Science and Engineering, National University of Singapore. This is my email address. My talk is on high performance thermoelectric. As you know, thermoelectric materials is related to the seebeck effect when the two sides of a conductor have different temperatures, the charge carrier distribution will be different. This will induce thermal current and the charge carrier accumulation either at the hot side or the cold side. So that this will induce a voltage between the two sides. The ratio of the voltage to the temperature gradient is the seebeck coefficient. Thermoelectric material can be used to harvest heat into electricity. The efficiency depends on the figure of merit ZT. Here S is the seebeck coefficient, sigma is the conductivity, S squared sigma is also called power factor. T is the absolute temperature, kappa is the thermal conductivity. For the technology to harvest the heat, thermoelectric conversion is probably the only plausible method to harvest the low-grade heat with the temperature below 200 degrees Celsius. To harvest this low-grade heat is important because the weighs about 2/3 of the total waste heat on Earth. The conventional thermoelectric materials are inorganic materials. They have P-type or M-type thermoelectric materials. Depends on the charge carrier. Thermoelectric materials that have high ZT value, but they also have some problems. For example, they have high thermal conductivity. They are usually expensive, and they are consisted of gas elements or even toxic elements. In addition, they have poor mechanical flexibility. Thus, they are not a good material for the flexible electronics. Hence, thermoelectric polymer gained great attention because of their unique advantages. Their thermal conductivity is lower than inorganic thermoelectric materials by 1 to 2 orders by magnitude. Their polymers can be cheap, and they are consisted of non-toxic and abundant elements. They can have high flexibility, so that they can be used as portable or even wearable thermoelectric generators or petty coolers. However, thermoelectric polymers that have lower thermoelectric properties than inorganic counterparts. By 2017, the highest Z value is only 0.25, and the corresponding power factor is 325 megawatt per meter per K squares. The Z value is significantly lower than that of inorganic counterparts. In addition, for the practical application, the Z value should be greater than 1. In this review article, the authors summarize the relationship between the seebeck coefficient and the electric conductivity of polymers. The seebeck coefficient decreases with the increasing conductivity and basically is proportional to 1 over conductivity to the power of quarter. The power factor is linear to the square root of the conductivity. When the conductivity is higher, the power factor. So that is important to enhance the conductivity and the seebeck coefficient of P dot PSS. Our early work to enhance the conductivity of P dot PSS was carried out on Clavis P. We invented a couple of methods such as through treatment with salt, sweet ions, or acid or cold solvent, or by adding surfactant into P dot PSS aqueous solution. Through this treatment, the conductivity of P dot PSS can be up to 200 Siemens per centimeter. In 2011, we noticed a new grade of P dot PSS. It's called Clavis pH 1000, and a work reported by Carl in Germany. They reported the two-step method. The first method is to add ethylene glycol into Clavis pH 1000. This step can increase the conductivity of P dot PSS to 600 to 800 Siemens per centimeter. Then the second step is a post-treatment of P dot PSS film in ethylene glycol bath, and then anneal at 120 degrees Celsius. Through these two-step treatments, they observe a conductivity of about 1,400 Siemens per centimeter. This is the highest conductivity for P dot PSS by 2011. In 2012, we report our work to treat P dot PSS by sulfuric acid. When we use 1.5 mole of sulfuric acid to treat P dot PSS, the conductivity can be enhanced to about 2,400 Siemens per centimeter. If we repeat the treatment for 3 times, the conductivity will be higher than 3,000 Siemens per centimeter. So this is the highest conductivity for P dot PSS by 2012. We also studied the charge transport mechanism by measuring the resistance with the temperature. When the temperature is below 230 K in this temperature range, the charge transport follows the one-dimensional variable range Hobby model. But when the temperature is higher than 230 K, the resistance becomes insensitive to the temperature. So this indicates that the transport mechanism become metallic or semi-metallic. This is also the first time to observe the metallic or semi-metallic behavior on transparent conductive polymers. We propose such a mechanism for the sulfuric acid treatment of P dot PSS. Proton can be transferred from sulfuric acid to the polyanion PSS because sulfuric acid is a stronger acid than PSSH. Then after this polycation become neutral PSSH, the Coulomb attraction between P dot and PSS will disappear. And because P dot is hydrophobic while PSS is hydrophilic, that when PSS become neutral, then the PSS will have a phase segregation from P dot PSS, and it can be washed away by water. The phase segregation can induce the conformation change of the P dot chain as well. In this review article by Professor Shu, they list the milestones for the conductivities of P dot PSS field. These two values were reported by our lab in 2012 and 2013. In 2014, a lab in South Korea observed the conductivity for about 4,400 Siemens per centimeter by treating P dot PSS with a fumed sulfuric acid. We are happy to say most of the secondary doping methods to enhance the conductivity of P dot PSS were invented by our lab at the National University of Singapore. After we enhance the conductivity, then we need to consider the power factor. For thermoelectric material, as you know, the Seebeck coefficient and the conductivity are interdependent. If we increase the carrier concentration, the conductivity will be increased, but the Seebeck coefficient will decrease. Thus, there is an optimal power factor. After we get high conductivity, then we want to dedope the P dot PSS to get the optimal power factor. For conductive polymers, there are two types of doping. One is a proteinic acid doping, another one is a normal oxidation doping. The proteinic acid doping can be dedoped by a base like sodium hydroxide, while the normal oxidative doping can be reduced by reducing agents like glucose and ascorbic acid. Our experiment indicated to dedope the proteinic acid doping is more effective to enhance the Seebeck coefficient than the normal reducing agent. This is our work for the sequential treatment of P dot PSS. The first step is to enhance the conductivity of P dot PSS through a sulfuric acid treatment. Then we lower the doping level by a treatment with a sodium hydroxide. This is the dependence of the Seebeck coefficient and the electric conductivity with the concentration of the sodium hydroxide. This can increase the Seebeck coefficient but decrease the conductivity. This is the power factor. At the optimal power factor, the Seebeck coefficient is 39.2 microvolt per K, and the electric conductivity is 2,170 Siemens per centimeter. The optimal power factor is 334 microwatt per meter per K square. Then we consider, can we further increase the Seebeck coefficient while not lower the conductivity too much? We consider to coat a layer of ionic liquid on the acid treated, then base treated P dot PSS. Why do we consider ionic liquid? Because ionic liquid can have high ionic thermal voltage and lower thermal conductivity. So we hope the ionic liquid can help improve the Seebeck coefficient of P dot PSS. It really works. So the Seebeck coefficient of acid treated P dot PSS or acid then base treated P dot PSS is enhanced. The highest Seebeck coefficient is close to 70 microwatt per K. The electric conductivity is lowered because of the dedoping. This is the power factor. The optimal power factor is 350 microwatt per meter per K square. The corresponding Seebeck coefficient is 68 microwatt per K, and the conductivity is 1630 Siemens per centimeter. We also measured the thermal conductivity. Then we found that the ZD value is 0.75. Why a layer of ionic liquid can enhance the seebeck coefficient of P dot PSS? We propose such an energy filtering mechanism. Under a temperature gradient, the charge carriers in P dot PSS accumulate. The holes accumulate at the cold end. The ions in the ionogel layer also accumulate. The cation accumulate at the cold side as well. The cation can block the holes with low energy so that it increases the mean energy of the accumulated holes at the core side. Thus, this increases the seebeck coefficient of P dot PSS. We further demonstrate that the seebeck coefficient is due to the holes instead of ions. We connect the P dot PSS with a layer of ionogel to an external load. Then we found that the output voltage is flat with the time. So this indicates it's not that because of ions. If it's ions, the output voltage should decrease with the time. We also investigated the stability of P dot PSS with the ionic liquid. The stability, both the seebeck coefficient and the electric conductivity are quite good. Then we consider how can we immobilize the ionic liquid, although ionic liquid is stable, but it's a liquid. We make this an ionogel, so we use a polymer called PVDF-HFP to immobilize the ionic liquid. This picture shows a film of ionogel. It's a freestanding film and has a high transparency. This is the dependence of the ionic conductivity and the thermal voltage on the ionic liquid loading. At 80% of the EM/DCA loading, the ionogel has a thermal voltage of 26 millivolt per K, and the ZT value is 0.7. We also demonstrate its application in ionic thermoelectric capacitors. So when the heat is turned on or turned off, then we can observe this kind of output voltage. Then we consider other materials as the gelatin. We consider the oxide nanoparticles because oxide nanoparticles can enhance the ionic conductivity. When we use silicon oxide nanoparticles as gelatins, we observe the improvement in the ionic conductivities by 1 to 2 times. The ionic conductivity of the ionogel depends on the loading. Also, the size of the silicon oxide nanoparticles. So this is the dependence of the thermal voltage on the silicon oxide nanoparticle loading. The thermal voltage is basically lower than that with the PVDF-HFP, but the ionic conductivity is higher. The thermal conductivity does not change too much with the silicon oxide loading. It's always low. So that we get the optimum ZT value is about 1.5. So this is higher than the ionogel with the PVDF-HFP. Our next work is to develop stretchable ionogels. for the flexible electronics. In this case, we use WPU. This is an elastomer as the gelate. So this is gel films. It could be stretched or twisted. The elongation at the black could be several 100%. This is the dependence of the Seebeck coefficient, the thermal voltage, and the ionic conductivity on the ionic liquid loading. The thermal conductivity does not change too much with the ionic liquid loading. So at 50% of the ionic liquid loading, the ZD value could be higher than 1. I also would like to mention that the ionic conductivity and the thermal voltage of these ionogels, they are hardly affected by the stress. So now after we studied these two types of materials, thermoelectric polymer and ionogels, we consider how can we combine the advantage of the electronic conductor and ionic conductor together. As I just mentioned, the ionic conductor like ionogel, they can have high thermal voltage, and they can be used in ionic thermoelectric capacitors. But the ionic thermoelectric capacitor can generate electricity only during the variation of the temperature gradient. If the temperature gradient is stable, no electricity is generated. In addition, their optimal external resistance is quite high, several orders higher than the thermoelectric generator. Then we invented a device is called the hybrid ionic electronic thermoelectric converter, HTEC in short. For this device, it has two layers. The bottom layer is an electronic conductor, like PEDOT-PSS. The top layer is ionogel. We use EM, IM, DCA, and PVDF, HFP ionogel. Then for this one, the VOC, we can observe this kind of stable voltage. This is due to the Seebeck effect of the electronic layer. And we can also observe this kind of peak voltage and the decay of the voltage. And the voltage volley and the increase of the voltage. This kind of behavior depends on the loading of the ionic liquid in the ionogel. It also depends on the resistance of the electronic layers. So this HTC, it can generate electricity and the temperature gradient. This is due to the Seebeck effect of the electronic layer and during temperature fluctuation, owing to the ionic accumulation variation of the gel layer. We propose such an operation mechanism for HTEC. There are 5 stages. So at each stage, the behavior is related to the ionic and the electronic coupling of the two layers. Then we investigate the output power on an external load under such a trapezoid thermal cycle. The output power of the HTC is 4 times or more than the control TEG with P.PSS, and the optimal external resistance of HTC is quite close to that of TEG. If a triangle thermal cycle is applied to HTC, then we can see this kind of voltage profile. So also, so this is different from that on TG. Let me briefly summarize my talk. We investigate the thermoelectric product P.PSS. At first, we try to enhance the conductivity. Then we try to optimize the power factor. We also studied the thermoelectric property of ionogels. Then to combine the advantage of the electronic conductor and the ionic conductors, we invented such a device is called the HTC. I would like to thank the group members for their hard work on the research projects, particularly to Dr. Yi Jie. She did most of the research work on the conductivity enhancement, and Dr. Zhenfa, Hongyin Yao, and Xin Guan. They did research work on the thermoelectric polymers, and Dr. Chen Halin, Dr. Xu He, and Dr. Yue Laifang. They did research work on the thermoelectric ionogels. I also would like to thank the fund agency for the financial support.